Okay, let's dive into this explainer and uncover the terrifying power and hidden beauty of mathematical patterns. We often think of math as just this rigid collection of rules and isolated numbers. But honestly, when you look a little closer, it's really just the study of patterns. Patterns that can literally describe the geometry of the universe, predict explosive growth, and even let us peek into the concept of infinity itself. So today we're going to build up your analytical toolkit. We'll look at the mechanics behind mathematical series, how numbers expand, how they step up linearly, and how they multiply exponentially. And to tie it all together, we're going to start with one of the most famous legends in the history of math. Right, so the origin of chess brings us this amazing story. According to the legend, the game was invented by Sissa ben Dahir, who was the vizier to the Indian king Shiram. The king was so absolutely blown away by this new game that he asked Sissa, "Name your reward, anything you want." And Sissa's request, it sounded incredibly humble. He basically said, "I just want some wheat. Put 1 grain on the first square of my chessboard, 2 on the second, 4 on the third, 8 on the fourth, and so on." He just wanted the amount of wheat to double on each consecutive square across the 64 squares of the board.
Naturally, the Ting agreed instantly without doing any calculations. He probably thought, wow, getting off easy. A few handfuls of wheat, no problem. But he completely failed to recognize the terrifying pattern of exponential growth. If we assume an average grain of wheat weighs about 50 milligrams, the real mystery is just how much mass are we talking about by the time we hit square 64? To figure this out, we obviously can't count grains one by one. We need a system. We need algebra.
To solve our chessboard mystery, here's what we'll cover in our toolkit today. First, the chessboard legend. Second, the binomial theorem and patterns. Third, arithmetic progressions. Fourth, geometric progressions. And finally, the infinite series. Moving right along to section 2, binomial theorem and patterns, or what I like to call the geometry of algebra. I love this quote by Professor Raman Primala. She says, "Math has the beauty of poetry. Its abstractions are combined with perfect rigor." And that hits the nail on the head. When we take a binomial, which is just a two-part expression, like x plus 1, and we raise it to a power, the result isn't just random mathematical noise. It actually unfolds into a beautifully rigorous, perfectly symmetrical pattern. And that symmetry gives us Pascal's triangle. Just look at how elegant this is. Each number is simply the sum of the two numbers directly above it. If you look at the coefficients, the numbers that multiply our variables when we expand a binomial, they form this exact shape. Take row 4, for example, 1, 4, 6, 4, 1. Where did that 6 come from? Just add the 3 and the 3 from the row above. Now, we call it Pascal's triangle in the West, but fun fact, this universal pattern was actually documented centuries earlier by brilliant Chinese mathematicians like Yang Hui. So why does this matter? Well, by following the steps you see here, you can totally bypass tedious multiplication. I mean, nobody wants to manually multiply x plus 1 by itself 4 times, right? It takes forever, and you're almost guaranteed to make a silly mistake. Instead, use the pattern. Grab the coefficients for power 4, 1, 4, 6, 4, 1. Then just cascade the powers of x down, 4, 3, 2, 1, 0. While the powers of 1 go up, boom. The result instantly falls out as 1x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. It is a massive time saver. All right, section 3, arithmetic progressions. This is where we explore the power of linear growth. Unlike algebraic expansions, this is about numbers stepping up or stepping down in a straight line. The crucial thing to remember here is that the jump between terms remains constant. We call that jump the common difference, or just D. So if your first term is 5 and your common difference is 3, your sequence is just 5, 8, 11, 14. You're just adding 3 every single time. It's steady, it's predictable, it's linear.
Now, take a look at this number, 50/50. This is the exact sum of all whole numbers from 1 to 100. And there's an amazing story behind this. It was famously solved in seconds by a 10-year-old Carl Friedrich Gauss. The legend goes that Gauss's teacher just wanted half an hour of peace and quiet, so he told the class to add up every single number from 1 to 100. Almost immediately, little Gauss raises his hand with the answer. He didn't sit there going, 1 plus 2 is 3, plus 3 is 6. No way. He spotted the hidden pattern in the progression. Gauss realized that if you write the sequence forwards from 1 to 100, and then backwards right underneath it, every vertical pair adds up to exactly 101. Multiply that by 100 terms, chop it in half, and you get 50/50. That brilliant childhood shortcut gives us the sum formula, or SN, that you see right here. So the first formula lets you find a specific term in a sequence, but that second one lets you find the total sum of the entire sequence instantly.
Let's actually apply this to something real, like predicting a salary. Say Tatiana starts a job at $10,000 a year. That's our A. And she gets a $500 raise every single year. That's our D. If we want to know how long it takes for her to earn a total of $122,500, we just use that sum formula. We plug in our numbers, solve for n, and it actually gives us a quadratic equation. Once you factorize it, it reveals it takes exactly 10 years to hit that mark. Just like that, math turns a messy, real-world timeline into a perfectly precise calculation. Okay, section 4, geometric progressions. Fasten your seatbelts, because this is where we get into explosive exponential growth.
So arithmetic progressions were nice and steady, right? Geometric progressions are a whole different beast. They compound, they scale rapidly. Because instead of adding a common difference, we're multiplying by a common ratio, which we call r. If we start with 2 and our ratio is 3, we don't add 3, we multiply. 2 times 3 is 6. 6 times 3 is 18, then 54, then 162. The numbers absolutely skyrocket. By the way, this is the exact mathematical model for how a single biological cell divides to eventually form complex life. Now, we finally have the tools to go back to our chessboard. Sissa Ben Dahir asking for doubling grains on 64 squares. Square 1 had 1 grain, square 2 had 2, square 3 had 4. This is a geometric progression where our first term is 1 and our common ratio is 2. The king thought he was giving away maybe a couple of sacks of wheat. So what is the actual sum of 64 squares of doubling wheat?
By using a clever trick, basically subtracting the series from itself multiplied by the common ratio, we get this staggering total, 2 to the power of 64 minus 1. Almost every term in the middle cancels out perfectly, leaving just the massive final term minus the very first term. And what does 2 to the 64th power actually look like in the real world? It equates to approximately 460 billion tons of wheat. To put that insanity into perspective, the entire world's annual production of all cereals combined today is only about 1.8 billion tons. Sisson was asking for hundreds of times more wheat than exists in the modern world. The king got completely scammed, all because he couldn't wrap his head around the explosive power of a geometric progression.
Let's wrap up with section 5, the infinite series. Let's see what happens when we really push the limits of logic.
Everything we've looked at so far has stopped eventually. 64 squares, 10 years of salary. But what happens when a sequence literally never stops? Surprisingly, we can actually calculate the exact sum of a never-ending list of numbers, provided it behaves in a very specific way. Now, I know that sounds impossible. If you keep adding numbers forever, shouldn't the total just get infinitely huge? Well, yes, unless the numbers you are adding are getting progressively smaller and smaller. The absolute key here is the common ratio. Infinite convergence only works if your common ratio is a fraction between -1 and 1. Imagine your ratio is 1/2. You're adding 1/2, then 1/4, then 1/8, then 1/16. The pieces you're throwing on the pile are shrinking incredibly fast. So as you approach infinity, the sequence converges. The sum hits a hard mathematical ceiling. But if the ratio is greater than 1, like our doubling chessboard, the terms explode. That's a divergent series, and you cannot find a finite sum for it. Before we wrap up this explainer, I want you to ponder this deeply weird mathematical paradox. Look at this sequence: 1 minus 2 plus 4 minus 8 plus 16. Depending on how you group these divergent terms, the math argues the sum could be positive infinity or negative infinity. But if you manipulate the series algebraically as a whole, it somehow spits out the answer 1/3. It's wild, and it perfectly highlights why rigorous rules in math are so absolutely crucial. Without them, infinity just breaks our logic. So what do you think? Does infinity have a true measurable shape, or is it just waiting for us to find the right pattern? Thanks for diving into this explainer with me today.